And hello world. I had to run up and get my power cord. That's what's going on in the real world here. Welcome. Let's get going here. Super and boom. Welcome. All right. We're ready. Let's do it. Good morning and welcome. We're live from Santa Barbara. This is CS-030 Java programming. We are broadcasting for Mayterm from Winter Hall. Live with a studio audience. This is a part of a 5-week seminar class, and today's lecture is scheduled for 2 hours. We're communicating in real time on Slack for those folks that are on our Slack channel and following in real time at #broadcastquestions. We are, and this is going to be archived on YouTube. Great. So let's take a moment to catch our breath. Turn off our notifications if we've got them. Make sure mine are good to go. Make sure everything looks good in the presentation. And take a moment to look at the bigger picture of things that we're working on. We've been talking a little bit about regulation and legal regulation and social norms and economics and the way all those things regulate us. And you can kind of put them together in this picture where we're at the center of a Venn diagram. Academics love Venn diagrams. And so you can think about you and your community at the center of a regulatory scheme that involves things that we usually think of as regulations in the law sphere, but we're also subject to various kinds of pressures from social norms, and we're also subject to various kinds of pressures from market forces. These also dictate and regulate our behavior. And perhaps the one that's most interesting and novel from our perspective is this idea that code is also regulating our behavior. And that's because code is becoming more and more an integral part of the world that we live in. So last time we thought a little bit about social media. You know, that's something that that's near and dear to our hearts in our phones and the way that we interact with each other. But what about your experience at an airport? Have any of you gone to an airport recently and had to check in? I don't have a good, how many of you have been through a security line at an airport? Okay, most of you have. Anyway, what is that experience like?
Depends on which airport.
Okay, let's.
Yeah,
So,
yeah, it is.
Why?
Because you don't have to take off your shoes, you don't have to take off your jacket, you just put your thing in.
So,
Oh, good citizen.
Yeah.
Thank you.
so
They treat you better.
TSA PreCheck is awesome. You get to go through it. How do you know? How does it happen that you are validated as being in TSA PreCheck?
I had to go
Do your fingerprint, you get a background check, and then your social security number is put into a database. And all of a sudden, code starts to regulate your behavior at the airport. You show up at the desk, and based on what the database says, you go left or you go right. And if you showed up in the database, wow, it's a totally different experience. You don't have to take off your shoes, you don't have to undo your laptop, depending exactly on what's going on. You kind of get whisked through really fast. It's really nice.
But then they randomly
Yeah, just to make sure that you're still having a terrible airport experience every now and then.
just to make sure that you're grateful for your hat for
Yeah,
when
yes,
it goes
yeah.
well.
That's it.
Who randomly chooses?
The rule government.
This, well, yeah, the Queen of England. No, the software does, right? The software chooses a random number generator if it's done well, or is just choosing randomly whose behavior, whose physical body gets regulated differently, right? I think one of the things that's really striking in the airport domain is the degree to which our physical body is involved with the whole enterprise. You know, you're electronically searched, you know, with a shortwave radar or whatever we're using right now, if you're not TSA PreCheck. And you know, you're scanned, your body is scanned and gates open and you can walk through or you can't walk through depending on which database you're in and depending on what the software tells you. And so now, of course, this doesn't exist by itself. The software is there for reasons, and the software is there as a reaction to social situations and as a reaction in some cases to legal, not so much market forces, maybe in some extreme it's a market force, but also legal implications as well. So saying that our behavior is regulated by code doesn't suggest that it's exclusively code, right? Code and social norms and law and market forces, they all work together. But increasingly, because there's so much software in everything we do, the code that we write is dictating our behavior, and the airport is one that's really extreme. A couple other ones we'll look at going forward as well, but the reason why we're talking about this is because the work that we do in learning how to code is going to have these implications in the real world. We're going to end up taking these data structures that we're working on and we're going to be implementing them for some purpose, for some end. Maybe it's the database that's keeping track of pre-checked people are going to be in a big hash table. Databases can use something like a hash table in order to keep track of the people in them. And so, okay, what are the implications for doing something with a hash table? What's the implications for the thing that we're building, and how do we want to put regulation? What kind of things do we want to regulate? Because at the end of the day, law, as we traditionally understand it, is just reified morality, right? It's a political process where we decide what is right and wrong. And if you think about social norms as just being a social way of determining what's right and wrong, market forces, maybe, I'm not sure that could be categorized so much as saying that what's right and wrong. But what is? Market forces, you think the market is a natural phenomenon?
Not always, but a lot of what it displays is based on nature. Like everything outside of that comes from monetary policy, or like bigger tools that are shaped.
Oh, well, it depends exactly what you're talking about with market forces. But I'm not thinking so much about like monetary policy. I'm just talking more about a market that sets prices based on people with supply and demand.
That should be more or less natural, yes. Unless,
No, it's not natural at all. I don't think it's natural at all. You have to set up them. People set up markets, right? The currency that you exchange is something that people create. If we didn't have currency, you wouldn't have a market. You know, there are all kinds of ways in which people create markets, and we can create them that work in different ways as well. And I think that's something that we kind of forget as we are like looking at all the social problems around us, that the markets are up to us to decide what the rules are for the markets. So we don't have to. We can encode the cost of externalities if we want. We can say you have to price in the cost of pollution, or you have to price in the cost of insurance, or you have to price in the cost of providing healthcare for everyone if we want to, because that's just, we set up the markets. And the nice thing about markets, though, is they're really, really efficient at distributing goods. So like I'm kind of in the camp that market forces and capitalism for the most part have done good for us, but we also still have a lot of power in setting up what those markets do and how they operate. I think we forget that a lot of times. We can fight about it. Fight about it, sure. Okay, so for the course, you guys have just gone through a big push last night. We have coming up an exam on Friday, so we were talking before we went live here what the parameters of the exam are. The exam is scheduled for 2 hours. It's got 98 multiple choice questions in it, and because of all the variables that are going on for this exam, it's going to be a large exam, but it's just going to be multiple choice. The folks that are taking it remotely, about half of you have trialed the software with Proctor Free. That might have been because I hadn't given you the password to get in until I sent out an announcement. But the password is live from Santa Barbara with capital L, F, S, and B. I'm broadcasting this on the internet, so I'm not exactly sure why I'm bothering to have a password. But anyway, we'll do it. Mostly it's just to test the technology for now. So that's the same password for doing the trial, and that's also the same password for dropping into the exam. So for the remote participants, you have a 12-hour window, technically a 10-hour window in which you can start the 2-hour exam. So you can start it at the same time that we start it in class, or 10 hours after that to accommodate time zone shifts wherever you are. So it is a timed exam too. So make sure that you have found a spot where you have good internet connection, where you're free from interruptions, where you can sit down and do the 2-hour window that you've got. Proctor Free, of course, is a recorded session, so I'm going to get a webcam recording of you taking that exam, in addition to screenshots of your environment. And also, for those of you that are taking it remotely, I'm asking you in the beginning of your exam to do a room sweep, which is a term that these remote proctoring services use to describe picking up your webcam and showing the entire room before you start your exam, so that I can make sure that there's not 5 tutors behind the screen, or I don't know. just to make sure that we're giving an exam with integrity. You're welcome to use scratch paper, but not other computational resources. And at the end of the exam, I'm also asking you to just show your scratch paper to the webcam. Again, just as a process. Okay, following up on that, we have a programming assignment on Chapter 15 due Sunday, and a quiz due on Monday, and there's no class on Monday because of Memorial Day. And any questions? Enjoy your Memorial Day with all that other stuff. Any questions about administration? For those of us that are in person, we'll be taking the exam here or in another proctoring location, depending on your situation, on paper. Okay, great. So last time we looked at the linked list, and we implemented the linked list in class. And this diagram here is designed to visualize what was happening in the software as we did our various coding to implement the linked list. And there were a couple things to just draw out from that, but one is that we actually had two different classes that we were three if you count the iterator. But the class that the application programmer got to work with is this one, linked list. Ooh, second grader drawing on the slides. This one, the linked list, is the one that you implement, that you instantiate with the new command. And then these myNode classes are things that the linked list class takes care of itself. And so the user of this class never actually works with the myNode. Those are just classes that are convenient for implementing the abstraction of the list. As we were creating new nodes, what we would do is we would create a new myNode object. We would set the data to whatever it was that the user wanted to store, and then as the linked list implementer, we would clean up the links so that the chain was maintained wherever we wanted to put that element. So at the end of the day, what we would have is we would have this data structure that had chain chunks of memory that we could walk down to find the zero element. In this case would be strawberries. The index 1 element would be mangoes. And then eventually we would get to the end of the list, and next would point to null, and we know we're at the end of the list. So one thing that was a side effect or a consequence of the way in which we decided to build this architecture is that it took a long time, well, relatively speaking, it took a long time to find a particular element in the chain, because we didn't have a way to go directly to the element, for example, that had blueberries, this one here. If we wanted to find the fifth element, or the element with index 4 in this case, we had to walk down that list by having some kind of a walker reference that would first point to the first one and then the second one by following the .next, 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 .next. And we would have a while loop until we ended up at the index 4 element. And then we could do whatever it was we wanted to do there. We could insert something, we could retrieve the data, our iterator maybe would hang out there. And so this is one way of doing a linked list. This is called a singly linked list. Anyone have a reason? Anyone have a guess why? Right. So because it only goes one direction, it's called a singly linked list. Each node has a single link. I'll show you a diagram later in the lecture of a doubly linked list, and this is where not only do you have a next, but you have a previous, and your linked list parent class there has a first and a last. So you can drop in at the beginning or the end of the list. It's a little bit more administration or when you're adding and removing elements, but it can be a little bit more efficient for like your iterator in particular. Okay, so today what we want to do is we want to continue looking at how the implementation of data structures impacts the efficiency, but not the abstraction of the different things that we're making. Again, before not last lecture, but the lectures before that, we were acting as if we were applications programmers. We were talking about what do these data structures provide as someone who wants to use a list or use a set or use a queue. But yesterday and today we're acting as systems programmers, as someone who is creating a class and saying, well, I know what the abstraction for a list is. How do I provide that service by creating instance variables and methods that support that behavior that that class is supposed to encapsulate? So classes, when you instantiate elements of the same class, creating lots of objects, they all share the same behavior. And that's a byproduct of the way in which our methods work. So we looked at linked list last time. I've got them backwards on my slide here. And today what I want to do is look at an array list and implement that. The array list is going to have the same interface. because it also is going to have the same list style behavior. List is an abstraction. It's not an implementation. It doesn't say how are we going to do the list. What it just says is what is the behavior of a list. And then the array list encapsulates both the data and the methods together that we need in order to implement that abstraction. And so we're going to do it differently than the way the linked list was built. And let's see. So I think what we'll do is we will just let me show you what that's going to look like before we drop into it. That's our linked list. Whoops, sorry, that's wrong slide. There we go. So our array list conceptually is going to be slightly different. Instead of having chunks of memory that are chained together, we're going to create one big chunk of memory using an array that can't change size until we reallocate that whole chunk. And so instead of making new bits of memory every time we want to add something new, we're going to have this storehouse of memory represented here by this line of elements we've got there. And some of them aren't going to have anything in them. So like this last element here doesn't have anything stored in it. But we have the memory standing by. We have capacity to put something in it. And so we're going to add this additional variable called size. And that's going to represent 1, 2, 3, 4, 5, 6, 7 elements that are currently stored, even though we could possibly store 8 without allocating new memory. It's a little different. And what it means is that finding a specific element is going to be very fast. So we know exactly where in memory this is located because all that memory is continuous. So if we want to find the index 4 element, we can find it immediately. If we want to add something, though, it's going to be a little bit trickier because if we want to add something to this spot in between these two elements here, we're going to have to take each of these elements and shift it down so that we have space to put something in this location. And that shifting takes time that wasn't necessary in a linked list, because in a linked list, you just had these chains that you just had to break the chain and scoot it in. But in this one, we have to move everything down in order to make space for this new element. Okay, ready to give it a shot? All right, so let's go back. Where were we? Implementing ArrayList, great. All right, here we go. Let's drop into Eclipse, and I'll share it with you if you're interested in watching live. And what I did is for those of you who are remote, I dropped the code from last class into Canvas. It is linked under the module from yesterday. Today, what I did is I copied the same code that we had yesterday into another project called 14 Basic Data Structures number 2. I'll come online and share with those of you who are interested. And what we're going to do here is we're going to build out our array list. And what we're going to do that by following our strategy. Let's see, following our strategy. What is our strategy? Well, let's see. Looks like I screwed up my slide for the strategy. Where is it? Don't know. Okay, well, our strategy is pretty straightforward. The first thing that we do is we describe what it is we're trying to achieve, and we do that with our interface description. So in this case, we've already described what our interface is. Our interface is our list. That describes the behavior that we're trying to achieve. Add, get, remove, size, clear, print, get iterator. The next thing that we do is we stub out our class. Well, we've already done that too. We did that last class. So we've got a class that compiles okay, has all of the elements that are necessary in order to implement our list abstraction. And so now, because we have that, we can write tests against it that are going to test our implementation. Well, the thing that was pretty clever about what we did last time is when we wrote our tests in such a way that it was testing the list behavior, not something specific about our linked list. And so we can take each one of the tests that we did last time and just copy it. And rather than instantiating our list with a linked list element, we can just implement it with an array list element. And then we will keep the exact same tests, and if we conform to our list behavior, then we shouldn't have any trouble. All right, so let's see what we've got. So here's a ListIterator test. We're going to do that one last. Let's take each one of these classes that we already had. Let's copy them and paste them. And now that we'll call it ArrayList Patterson ArrayList. It's like the longest class name ever. Once I get these set up, I'll share the project with you guys. All right, ready? Here we go, sharing the project. Boom. Tim, Boaz, you're getting notices to accept? Okay, so we copied over those tests, but what we didn't do is we didn't change the implementation. So if we go to Boaz's, you can see that we have LinkedList there as the implementation that we're choosing. But we could just, because ArrayList and LinkedList both implement the same interface that we're using here, because we say list is of type RList, we can implement it with a different class if we want. There's ArrayList. Copy that. And I'm going to go through each of the other tests that we just copied, and I'm going to replace the LinkedList implementation with the ArrayList implementation. And let's see, I don't think I copied the ListIterator test, so let's copy that one as well. Now, if we take all of these and we run our test, what should we expect to see from this test at this point? What do you think is going to happen when we run our tests? That's a safe answer. It's accurate. So the things that will work will be the tests that we implemented last time, so the ones that are based on LinkedList. The ones that won't work are the tests that are based on ArrayList, because we haven't implemented that. We've just created a public interface for it. Again, the public interface are the things that applications programmers or API programmers, stands for Application Program Interface, that those users can use for our class. So I run the JUnit test, gives me a second to power up. And you can see that over here on our list of all these tests, the ones that are failing are the ones that I annotated with ArrayList. On and down the line. Because we haven't implemented ArrayList. So of course they're not going to work. It did compile okay though, because we stubbed out the public interface. It's just they're not returning anything that conforms to the behavior that we decided. All right, so let's see if we can build this out. We know that an ArrayList needs to have an array internally that's going to keep track of the elements that we have. And so when we first start, we're going to start with an array. Again, we'll treat this as an array of strings until we have more technical machinery to be able to do other things other than just strings. But we'll say that we'll have it'll be an array of strings called the contents. This is where we're going to store our data. And we're going to initialize that with a new string array, and we'll start with, let's say we'll just open it up with maybe 4 elements. So this means that at the beginning, when we create our array list, we can have 4 elements stored in the contents that we have. If we want to store more than 4, we're going to have to change contents and grow its size so that it can hold more elements. And in addition to that, we're going to keep track of the size of our size of our list. And so the size is going to initially start as 0. Now the reason why we need something separate called size rather than just the array called contents is because although we can store 4 things right now, we aren't actually storing 4, we're storing 0. And so size is going to be the location in our array where the next element is going to go. All right, so let's start by answering the question of what is the size of our array? This is the easiest one to do. Well, we're going to keep our size instance variable up to date. And so that's going to be what the size is. And what is our clear method going to be? Well, this is pretty easy as well. We just say size equals 0, and whatever was in our contents is now going to get overwritten when we continue to work with it. Print Save that for later. Get is going to be pretty easy as well. So the first thing that we have to do is we just have to make sure that where is within the bounds of our array, and if so, we return the element from our array. So we'll say if where is less than contents.length. Now, arrays work slightly differently. So in order to get the length of array, you say .length. But for you guys, you should remember the method to get the size of data structures is almost always .size with parentheses as a method call. .length is the array itself is kind of an anachronism from the days when C was dictating our syntax. So while if where is less than the contents.length, then we can just return contents sub where. So we ask what is, well, if we spell it right. So if we want the element at position 0, we just return the element at position 0. We just have to make sure that it's not too large. And if it is, we return that, sorry. And if we have asked for something, let's see, I guess we also need to check if where is greater than or equal to 0 to make sure we don't ask for something negative. All right, so if where is greater than or equal to 0, and or is not right, and where is less than contents.length, then we can return the correct element. Otherwise, we'll throw the no such element exception. And we have to import it. And we have to answer something else. Oh, that's not return, that's a throw. Okay, so get, that's easy. Clear, that's easy. Size, that's easy. Now we're going to have to deal with adding an element. So there are a couple situations that we have to worry about here. We have to worry about if we have enough space in our array to add an element. And if not, we're going to have to resize our array. And so let's create a helper method here called check contents size. And what that's going to do is it's going to see if we have space for one more element. And if we don't, then it'll double the size of our array and copy everything over. So after we call this, we'll know we have enough space. So now we know we want to put something at position where, so 0 through the length. And so we need to shift everything down from the position where to the right by 1. So we're going to need a little loop here that says for some index that's going to be the position where we need to start from. We're going to start from the end of the array. So we'll start at size, and we're going to shift everything to the right 1. So I equals size, and then we're going to say while I is greater than or equal to where plus 1, we will subtract 1 from I, and we will say that contents sub I should equal contents sub I minus 1. So that should shift everything to the right by 1. And now it's important that I did it from the end of the array, so from the right of the array, if you have to think of it that way, to the left, because as we shift everything to the right, we're not overwriting things. If we started from the left, yeah, well, if you started from the position where you wanted to insert and you moved it next to it, and then you move that one again, you would just fill up the entire array with one element. So you want to start at the end and bump it down. So then after we have made space, we can say contents sub where equals what, and size has increased by 1. Think about that for a second. I guess we should also have a check here to make sure that where is in bounds. So we want to make sure that if where is greater than 0, greater than or equal to 0, and where is less than or equal to size, because you should be able to add it to the very end of the list, which would be a new location. So the opposite of that, so let's use De Morgan's law here, because what we want to do is we want a condition where we're going to return with an exception. So De Morgan's law says that we are going to say we're going to take the negation of the whole thing. We're going to change the and to an or. And we're going to change the sense of the relation here. So greater than or equal to 0 is less than 0, and less than or equal to size, the opposite is greater than size. So we say if where is less than 0 or where is greater than size, oh, actually that was enough, right? If where is less than 0 or where is greater than size, then we want to throw in your exception. All right, so if we had an OK result and we make a little space in our array, then we shift everything to the right, we put our new element in, and we increase size. All right, so remove, we have to do the opposite. We have to shift everything down to the left one, overwriting the element that we want to remove. So let's make our check to make sure our location is in bounds. That's good. And then we need something like, we don't need to check content size because our content size isn't growing, it's shrinking. And so now we say, well, in this case, we're going to go the other direction. We're going to say, first let's capture the data. So the thing that we want to return is going to be contents sub where. That's the thing that we're about to delete. Then we're going to start at position where, and while we're less than, work with me, keyboard. Come on, there you go. While we're less than size, we're going to increment I. And we're going to say content sub I equals content sub I plus 1. We're going to remove 1 from the overall size and return the value that we just overwrote. Shifting everything to the left, overwriting the element that we just wanted to destroy. Okay? Following the logic? Sorta. Okay. So we have one situation then where we haven't handled it. That's where we would like to add something to our array, but we've already filled up all the space that we have allocated, which starts as 4. And so what we're going to do is we're going to have to write a new private function that helps us to manage our internal implementation called check contents size. And what this is going to do is it's going to say, do we have enough space to put one more element in? It doesn't return anything. It just has a side effect, which is that it's going to modify our internal data storage. Well, if size is less than contents.length, then we can just return because everything's okay. So if we currently have 0 elements in it and we have space for 4, we're okay. If we have 4 elements and if size is 3 and we have space for 4, then we're okay. But if size is 4 and our contents length is 4, we have a problem because we're going to put something into the 5th space, and so we need to upgrade our array. So here's what we're going to do. We're going to create a new, we're going to stand by, create our new array. We'll call this new array is going to be new, call it new contents. And we're going to allocate some space for it. It's also going to be string, but the size that we're going to allocate is going to be contents.length times 2. So we'll reserve twice as much memory for our new contents. So that's great. Now we have a place to put all our new data, but we have to copy over what we currently have. So we'll say for integer I equals 0, while I is less than contents.length, I++, so we'll walk down each one of the elements of contents. And we'll say new contents sub I equals contents sub I. That will copy everything over, leaving half of the array and new contents empty. Then the last thing that we want to do is we just want to move over and say contents equals new contents. So we will reference this new array. So we'll create an array that's twice as big. We'll copy everything from our smaller array into the bigger array, and then we'll say this new twice as big array is the one we're keeping track of. I feel like it's pretty good. Do you all feel like it's pretty good? That's great. Our feelings are worthless. What's helpful is if we have tests that validate whether or not our feelings have any validity. That's right, silence is gold. We can test though, because we've already written our tests. We're doing test-driven development, and so that means that we have a bunch of examples that we're ready to go. And we know that it worked in a linked list. So if we did our ArrayList implementation, some of them better pass. Now all of them aren't going to pass because we haven't done a ListIterator yet. But let's see what we get. Well, that makes me pretty happy. We passed almost all of them. We have a bug in our remove function that was revealed because of Tim's test that he wrote. We'll take a look at that. And we also have our ListIterator test is not passing. Well, that makes sense because we haven't implemented our ListIterator yet. Let's take a look at what failed here in the remove function. So as we look at the test, we're creating a new array list. So that's good. We're using the right implementation. We're adding eggs to our list at position 0. We're checking to make sure that the thing at position 0 is equal to eggs on line 17. That's good. That passed. We then remove element 0. That's good. It seems like we passed line 18. And then we expected a no such element exception to be thrown when we tried to get an element in an array that didn't have anything in it. So something went wrong with our get function when we had an empty array. So let's take a look at what we did. So where's our get? So we said if get is greater than or equal to 0, oh, we never checked we made a classic blunder here. This is the #1 blunder that you make in array lists. And I made the blunder honestly. It's not a setup for a teaching moment. I mean, it is a teaching moment, but it wasn't a setup. What's my error? I've got an error in my get function. How am I keeping track of how much data is being stored in my array? We've got two things going on. One, we have a capacity for how much data we can have, and the other is how much data do we actually have.
Size is how you keep track of how much data. If it has the amount of data actually has less than size, or 0, so it's more less than.
You're right. Size is keeping track of the amount of data that we have, and because we start with size is correct. Size is just right? So size is the number of elements that we have. Because our indexes are based on 0, if you actually use size as an index, that's the next spot where you're going to put some data. Our data actually goes from index 0 to size -1 at any given moment. So if size is how much data we have in our array, and in line 65 we call get, and then in line 66 we check to make sure that we're getting an index for data that we actually have, our bug is on line 66. What is the error? We have application programmers who are saying, hey, get me the element at position where, and we're checking to see whether or not in line 66 that index is valid. The first half is good, right? We know that where has to be greater than or equal to 0. So the error is in the second half. What's wrong with this piece right here?
Oh, it can't be both.
What do you mean?
It can't be both. Where cannot be equal to 0 and less than context.
It can. So like something 1 would be greater than 0 and less than context length as long as context length is high.
Well, if it is 0, but it is not less than context.
It's still less than context length. 0 is less than context length. The problem is that context length is the capacity of our list at a given moment. It's not how much data we actually have. So what we should be checking is not whether it's less than contents length, but whether it's less than size. That's the like, it's a textbook error, and I did it. I'm so proud of myself for making a textbook error. So we run our tests again, still not passing, but it's not passing for a different reason. That's good, I guess. All right, so now we got past line 19, which is the error we had before. In line 21, we're adding bacon. We're adding orange juice. Position 1 got bacon. We removed 0. Position 0 didn't end up being orange juice. So something happened when we tried to remove an element from our list. So let's just take a look and see if remove messed up somewhere along the line. So if we remove position 0, if where is less than 0 or where is greater than size, well, I guess it should be size minus 1 then, because we can't remove something from position size. So if it's greater than or equal to size, then it's out of bounds. Because if we have 5 elements in our array and we ask to remove the element at index 5, that's 1 more than the amount of data that we have. So the element that we ask to remove has to be less than size, strictly speaking, or greater than or equal to 0. So great. Real subtle error, right? Very subtle error. I had greater than. I should have had greater than or equal. Let's make sure that's right. And the test saved my bacon. Ha! Saved my bacon. Get it? The test saved my bacon. Although it didn't pass, but still, that's such a good joke. It saved my bacon. I need a laugh track. Hooray! Saved my bacon. That's the fake studio audience laughing right now. The people in the room can't hear it, so they don't even get it. Something's still not going right. I didn't even realize I made that one. Just natural. It's natural for me to be so hilarious. All right, something's still going wrong with removes. What happened? We tried to remove position 0. We got the element at position 0. That's okay. I equals 0. While I is less than size, size should be equal to 1. And we say contents I equals contents I plus 1. Size minus minus, return right. Something's not going right. I can't tell just from the code. So what I'm going to do is I'm going to put a breakpoint here, and we're just going to watch it happen. So we'll do a breakpoint. I'm going to right-click here and say debug that. It'll run our tests, switch over to debug perspective. Whoop. There we go. Okay, so we're in line 21. We can look and see what list currently has in it. It says 0 elements. That's good. So if we step over that line, if I do that carefully, step over, now we've got 1 element in it, should be bacon. Now we've got another element in it, and that should be orange juice, and orange juice should be position 0. Good. So we've got orange juice and bacon. We're going to step over the next line where we just get it. All right, that's good. Now we're going to remove position 0, and we better watch and see that our array removes orange juice and replaces, moves bacon down, and size should go down to 1. Here we go. Boom. Oh, what happened? Orange juice didn't move down. Orange juice went away, but it didn't overwrite bacon. So now we kind of have some idea of where to look for the problem.
What was it supposed to remove?
It's supposed to remove the 0th element, which was bacon. Oh no, did it do it right? Maybe you're right. Let's try that one more time. Maybe I was.
The element that was left was bacon.
Good catch. Okay, let's see. Let's try that again. Here we are. Got a little eager about it all. Okay, so here's our contents. Orange juice and bacon. We're going to get the first element, make sure it's equal to bacon. That's good. Position 1, not the first. We're going to remove 0. So 0 should be orange juice and bacon should fall off. Okay, that actually did work. You're right. And is size set to 1? Size is set to 1. So when we get position 0, is our test wrong? Yeah, our test is wrong, right? Yeah, I think our test is wrong. So if we do 21, we add bacon at position 0, and then we add orange juice at position 0 and bump bacon to the right. On 23, we check to make sure our bacon is in position 1. We remove 0, which is orange juice, so we should have bacon left. So our test is wrong. Okay, so we'll fix our test, but that means that now do we have a bug in our linked list? go back here. Let's just run this test one more time. Okay, we passed that test. That's good. But now we're suspicious of our previous implementations. Let's go back to here. Here are all the tests so far. Let's rerun those. Let's see, I'm not sure what I'm running. Let's just do it again. Oh, it all passed. How did we pass? Where's our list test remove Tim? How did we pass that? Oh, that's because it's a different test, but we know the test is wrong. Okay, so we know we had to change our test for. This kind of speaks to how we should probably range our tests slightly differently here, but we'll do that another time. But now we've discovered a bug in our linked list implementation. Again, this is why I love testing, although it's sad when we have an error. Okay, so what should we do? We know our array list is working cleanly. We have to implement our ArrayList ListIterator, and then we have to go back and see what's wrong with our linked list. Since we're sort of in the mode for ArrayList, why don't we finish our ArrayList implementation, and then we'll go back and see what we did wrong on our linked list. Maybe we'll take a break and see if we can figure it out on our own. Sound all right? Okay, so the one thing that in addition to the bug that we just uncovered in our linked list implementation, yay for testing, we also know that we're not passing our ListIterator class. That's down here. That's because we don't actually have one yet. So let's, just like we had a local class for a ListIterator in the linked list, let's do the same thing in our array list. And we're going to create a private class that's going to be an implementation of a ListIterator that we're going to use the ArrayList implementation to create. So private class, and we'll call it ListIterator. It's local. It's going to implement our public interface, ListIterator. Okay, so the first thing that happens is we have to include that. We have to spell it right. That's the first thing that happens. Then we add the unimplemented method, and we have to decide what it is we're doing. So now ListIterator is pretty easy in all things considered, because what we can do is we can just keep track of a particular position where our ListIterator is at. And so the ListIterator is a cursor, and so what we'll do is we'll keep track of the position one ahead of where our cursor is. So we'll have an integer that is our cursor, and it will start at position 0. Meaning we're actually before our position 0. So has next is just a question. All we have to do is say if cursor is less than size, then we can return true. Because if our size is 1 and cursor is 0, it means we're before position 0. We have one element, and otherwise we'll return false. All right, next is easy enough. Cursor plus plus, and well, let's see, and then we'll return contents sub cursor -1. If we want to add data, we're going to have to add the data at the position that we just, let's see, the position before our cursor. So then that should be easy enough, because that's just simply calling our parent class. We'll just say add to position cursor -1 data. And this needs to be our list. So let's see, how are we going to get that? Now that's going to be our parent. Let's see. How do we get access to outside of our class here? This is a problem I'm not quite sure about. Let's see. We want to qualify with the enclosing type. There we go. Ah, there we go. Great. All right, so that says we want to call the add of our enclosing class. And if we want to remove something, we just remove it from the element before. We're just calling the remove on our parent class because of an array makes this easy. And then set is about the easiest thing ever. We just say contents.cursor -1 equals data. And keep track of what the data was. And return it after we reset it. All right, now we'll just see how our, I feel like we need to throw some exceptions, but we'll see how our coverage works. All right, so we passed several of them. Where did we fail here? Null pointer exception on iterator.hasNext. Okay, that's no good. Let's see what happened. Iterator.hasNext, return true, return false. Oh, that's because we didn't actually return an iterator here. Sorry. Did that last time too. So our constructor, we didn't actually return an iterator. Okay, returning an iterator. Try running our test again. Almost passed. Let's see what. Oh, that's our linked list error. Here's our error. Something happened when we tried to add our durian. Thanks for that, Boaz. All right, so we used our iterator. We said has next. We said our next element was blackberries. We tried to add durian. We got position 1. It wasn't durian. So let's put a breakpoint here and see what happened. We probably just have an off by 1 error in our remove element, in our get, I suppose, in our add element. Okay, so we'll debug that. Open debug perspective. Go to our test. Actually, we need to look at add because add's not doing quite the right thing. So let's stop that. Let's try it again. All right, now we'll step into add. And we'll see cursor is currently, what is cursor currently equal to? Cursor is currently equal to 1. And we want to add to position 0 our data. I see. So perhaps we actually just wanted to add it at position 1. Try running that. Rerun our test. Open our debug perspective. And let's see. Run it. And how do we do? All right, I'm a little lost in our testing. Let's run that test. All right, get 1 worked, and then next did not equal papaya. So let's take a look at what happened after we added our element. We added our element, and then we need to, because we added 1, we need to add 1 to our cursor. That makes sense. That reminds me that we're going to need to subtract 1 from our cursor here as well, because we've changed the size of our list. Let's try that again. All right, here it is. We have a no such element exception. We tried to remove something from position 8. Let's see, where were we in our, what is even going on? Okay, let's, we had an array out of bounds error, so we didn't do correct testing here. This is when we tried to remove an element from our array based on our iterator, and something's not quite right with that. All right, so this is getting a little painful. Let's see, let's go back to our package explorer. Let's run our ListIterator for coverage. Okay, so we got as far as trying to remove blueberries, but we had a problem because something with our remove code didn't work right. So we said, well, I is equal to y, and I is less than size, contents I equals I plus 1. Okay, that means at the end of our loop, we're going to try and reference position size, and that doesn't exist, so we have to just stop at size minus 1. Because we want contents I to never be greater than size minus 1. All right, let's try that. Okay, so good, we're passing now. Let's go back. Let's try coverage of all of our tests and see how we're doing. All right, so we're passing everything except for the bug that we uncovered in our linked list. So that feeling that we had that our code was pretty good was completely misplaced. We had several bugs in our list iterator that were exposed by the fact that we had already written tests. They're the same tests that our linked lists were running. In the process, not only did we discover, in the process of writing tests, not only did we discover tests in our bugs in the implementation of our array list, but we discovered bugs in the implementation of our linked list as well. So we're about halfway through, and what I'd like to do is take maybe a 5-minute break to stretch and get some water, whatever we need to do. And then we'll come back and we need to figure out what's wrong with our linked list. Hopefully that's a straightforward fix. And then we'll move on and see how we can use these existing data structures now to implement some of our other data structures. And that's how we'll finish out for today. Any questions before we take a 5-minute break? No questions. Okay. Then we are good. We'll come back at 11:30. Okay, we're back, and one of the things that, as we were implementing our array list, one of the things that we realized is that we had a bug in our implementation of our linked list from yesterday, and that was revealed because as we tried to implement the tests for our array list, it didn't work, and when we dug in, we saw that the test was written badly. So we went back and we fixed the test, and this is the correct test now for linked list, and we see that it's broken for some reason, and it's broken because when we remove something from the beginning of the list, it's not working correctly. So during our break, I went to identify what the problem was, and the problem was located in, not surprisingly, the remove method of the linked list implementation. So if we go to remove, and we look at the code here, I've commented out the correct code. So we had this situation where we had a special case when we wanted to remove something from the very beginning of the list, and we could actually just remove the condition that the list was one element long. We could just say that it is in fact a special case whenever we want to just remove the first element in any capacity. And to do that, rather than saying that first equals null, we say first equals first.next, and so if our list does just have one element, it ends up being null anyway, which is what we had before. If we make that correction and we go to our JUnit test, we can run it. And huzzah, we pass all of our tests. So we believe and we have confidence that our tests are pretty well written. You can see that from our code coverage, we're actually not executing a lot of our code. We could improve our tests in order to do a little bit more code coverage by going to our remove code. And maybe, like for example, we could, actually let's just make a new test in the remove test Tim's class here. Make a second test. What we needed to do is we needed to remove things from lists that were longer. So we will just add something else. What else is for breakfast? Lucky Charms. Lucky Chars, that's a different breakfast cereal. Toast. We just can make sure that 0, 1, 2, 3 equals toast. Remove position 2, 0, 1, 2, and then we should make sure that now position 2 equals toast. And if we run our test again, it broke. What did I do wrong? 0, 1, 2, 3. When we remove the last element from our list, it's breaking also. Oh gosh. 0, 1, 2, 3. 0, 1, 2, 3. It's not even getting toasted correctly. This is painful. Oh no, so I got it backwards. Sorry. We had bacon, we had orange juice, we had Lucky Charms, we had toast. It should be bacon again. There we go. So the test was wrong. That makes me happy because I didn't want to go edit the code. I hope the test is wrong. We'll prove. All right, great. The test was right. And now if we look at the code coverage for LinkedIn tests, we see we have a lot more coverage of our remove method, which gives us confidence that the code that we wrote there is well written. Okay, great. So now, where are we? We wrote a list iterator for the array list, and just like linked list, we used that same abstraction. We wrote the list iterator for an array list. We used the same abstraction for list iterator because a list iterator operating over a list should work the same way regardless of whether it's implemented with an array list or a linked list. And so we demonstrated that. In both cases, we did test-driven development. We wrote our tests against the list interface, and because of that, we used the exact same tests as before. We just changed the data structure that we used to implement the list interface. And in doing that process, we discovered bugs. We cleaned up the bugs. Hopefully, we proved the point that writing tests makes your code more reliable. So we did implement array lists. Array lists keep the data in an allocated array of memory rather than as a chain of objects, so like a carton of eggs. And if we run out of memory, we need to reserve more. So that was the process of checking the array size that we wrote. The structure looks roughly like this. We had the array represented there by our collection right there. And as we fill things in, we put stuff into the next gray box. And if we run out of gray boxes, we have to double the size of our array. Great. We saw that when we added and removed elements to an array list, that was a little bit different than linked list. Because we had to, for example, in that egg that's X'd out, if we wanted to get rid of that egg, we had to shift all the eggs down to take its place. And so that's actually quite a bit of time for removing a particular element in the middle of the array. Tim?
What if you just shifted the last element into the spot?
That would be much faster, but that would violate our list abstraction, which is that order is preserved. So that would be like saying, let's put people in a line, Tim, Patterson, BB. Let's remove Tim, BB goes to the head of the line. That's not fair to me, right? Because the order's not preserved.
Unless you wanted to go last,
That would be great. That would be a different thing than a list. That would be PattersonPreference.com.
You'd be rewarded for coming first by going last if someone else came.
Okay, it's sort of like a biblical cue or something. The first is last. Okay, well, we implemented it. We dealt with the fact that we had to shift everything over. Worked out well. Did we pass our tests? Well, no, we didn't, to be honest. And when we went in to dig into it, we found out why, and we were able to correct our bugs. So now as we evaluate the efficiency of our linked list, it's very important to be able to understand, based on these conceptual approaches to these two different implementations, what the efficiency of these operations are. So the question is, how long does it take to get to the nth element of our list if we have a linked list? Some arbitrary element. Well, in a linked list, we have to have a loop that's going to walk down our chain. And so if we try and get to the nth element of our list, it's going to take n operations. We have to look at one element, and then the next element, and then the next element, and then the next element. And so it's linear in the length of our array. If our array is 1 million, it's going to take about 1 million operations in order to find the 1 millionth element. If we want to add or remove an element, though, and we want to add something, for example, to the beginning, if we want to add or remove an element from the linked list, it doesn't matter how long the linked list is. We can add an element to the beginning of a linked list just by creating a new node, assigning the next reference to the beginning of the previous chain, and we're done. That previous chain could be 1 million, it could be 1 billion, it could be 3 billion. The length of that chain doesn't matter because it takes a constant amount of time to add something to the beginning of the linked list. That's one of the real strengths of the linked list implementation. Now, what if we want to add something to the middle of the linked list? Well, then it depends on how long your list is. So if you have an iterator and your iterator is already at the position where you want to add something, it's constant time. You just add the node, you just put it together, and you're good to go. But if you have to get there and then add something, then it depends on the length of your array. An array list, how long does it take to get to a particular element? Well, it's constant. We just immediately access the element. We don't have to walk down the chain. We just use the subscripts in order to find the exact location. But how long does it take to add something once we have that location? It depends on how long our array is, because we have to shift everything to the right or to the left, depending on whether we're moving or adding elements. So the relationship is kind of inverted. In an array list, finding an element is constant time. In a linked list, finding an element depends on the length of the list. In a linked list, inserting something into a position, if you're already there, is constant time. But in an array list, inserting something into a position depends on the length of the array. So the efficiency of those operations is reversed. So we use something called big O notation in order to talk about how these different operations operate in terms of efficiency. Have you guys ever encountered big O notation before? What context? Python. Okay. We'll talk about it more in our algorithms class for sure. But it's the same thing. And what's important is that the time it takes to do these operations is independent of the language. So it doesn't matter if you do a linked list in Python or you do a linked list in Java. The efficiency of those operations is going to be the same because of the nature of the way the data is being managed. Yeah. Right. So selection sort was a great example. In order to sort a list, it took order n squared. So it depended on not just how long your list was, but it depended on how long your list was squared. So, right. So finding a position in a linked list depends on how long your list is, but not squared, which is good. So big O notation is just concerned with the rate of growth for really large inputs. So how long is the efficiency? How long is it going to take for an operation to happen based on eliminating constants and eliminating just constant arrays or constant multipliers. Mention the difference between a singly linked list and a doubly linked list. So one way in which the doubly linked list differs is that you have a link to the beginning and the end of the list. And you also, in each one of the nodes, you have a chain that goes forward and a chain that goes back called next and previous. So if you want to add something to the middle, you have to create a new node. And that's going to have a previous that's got to point to that one. And it's going to have a next that points to that one. And then you've got to break these chains here and make those point to this node and the next to point to that node. So again, even though you have another link there, it's just a constant amount of time excuse me, in order to add another node. But because it's doubly linked list, you might get a little bit more efficiency in adding something to the end of your list. Because if you have a special method that's add last, for example, you immediately can get to the end of your list by following your last reference. And you don't have to walk down the entire list in order to get to the end. And so that just supports having a special method called add last that would be very efficient. There's a small downside. The downside is that programming it takes a little bit more care because you have to manage next and previous links when you add and when you remove elements. It takes a little bit more memory. So every node doesn't just have a next reference, it also has a next and a previous reference. So it takes a little bit more memory for each individual node. But I think overall, there's not a big downside for using doubly linked lists. It's a little bit more efficient, and you can actually build on doubly linked lists to make more efficient queues, for example. You can do an efficient queue using a doubly linked list. That's harder to do with a singly linked list. So if we look at some of the operations, and in particular we look at the difference between singly linked lists and doubly linked lists, and we think about what you have to do in order to get to these different elements. And if we say, what does it take to access an element? For both a singly linked list and a doubly linked list, if we want to get to an arbitrary element in the middle of our list, it's going to depend on the length of our list. So if we want to get to like position n over 2, we're going to have to walk through n over 2 elements. And so it depends on how long our list is, regardless of whether it's singly linked or doubly linked. The double link doesn't bias anything. If our iterator is at a specific position in our list and we want to add an element to it, our singly linked list and our doubly linked list both take a constant amount of time. So we call that order 1. And what that means is if we want to add something, the process of adding something doesn't depend on how long the length of the list is because we're just concerned with the local neighborhood and the links between the local nodes. Because our linked list has a reference to the beginning of our list, if we want to add or remove something to the first element, it's also constant time. Because we just make our new node, we patch in our references to the first and to the previous and next, we're good to go. If we want to add a last element, well, in a doubly linked list, it's clearly constant time because we just follow our last reference and add it to the end, and we don't have to walk down the length of our list. If we have a singly linked list, it depends. It depends on whether our singly linked list is also keeping track of the end of the list as well. Singly linked list could keep track of the end just to support efficient adding to things at the end of our list. But if it doesn't, then it's order n. Because to find the last element, we have to walk down the entire length of our list to get to that position. That depends on the length of our list. And then once we're there, we can add something. So because of that, this table has a caveat. It says that adding an element to a singly linked list is constant time if we're keeping track of the end of the list. Otherwise, it depends on the length of our list to get to the end of it. Finally, if we want to remove the last element, a doubly linked list is constant time, but a singly linked list is order n. The reason why is to remove an element, you have to have access to the element right before it, because you have to splice out the element you want to remove. And even if you're keeping track of the last element, in order to get to the element before it, you're going to, in a singly linked list, you're going to have to walk down the entire array to get to the one before it. You could say, I'm going to keep track of the last element and the next to the last element. Then it would be constant time. But it's just, you're trading off complexity administration for supporting one particular element, one particular method. Excuse me. Okay, what about the efficiency between an array list and a doubly linked list? Now, this is the thing that I think is really important to understand. This is our trade-off. To access an element in an array list, we just use the subscript of the array in the implementation, so it's constant time. We just go to position n. In a doubly linked list, we have to walk down our array in order to get to that position, so that depends on the length of our list. To add or remove something at a particular position in an array list is always going to depend on the length of our list because we have to shift everything over, either to the right if we're adding it or to the left if we're removing it. But for a doubly linked list, we just splice in the piece we need. And then finally, in order to add or remove an element at the end, an array list is constant time because adding it specifically to the end doesn't require any shifting. And in a doubly linked list, adding something to the end specifically doesn't require walking down the list because we have a pointer to the last element. So both of those are constant time because the question is, are we adding or removing something to the last element? And the reason why there's a plus there on the array list is because every now and then adding something to the end of an array list requires us to double the array size because we ran out of capacity in the underlying array. And so we say that we're going to amortize the cost of doubling the array size over all of the elements. So it's constant time generally, more or less. Okay, understanding why these are the efficiencies of these two implementations is a really great starting point for understanding big O notation in general and understanding these algorithms. But we also mentioned a few other kind of implementations that we have in our Java collections framework as well. We have stacks and queues. And if you remember from our tree diagram, stacks and queues were white nodes in that box of whites and reds. And that's because they're interfaces. They don't specify an implementation. They specify a behavior. Remember, a stack has these additional methods, push and pop, that enable us to take something off the top and the bottom, put things on the top and take things off the top of our stack, like a stack of pancakes. And a queue just has this abstract idea of adding things to one side of a queue and taking things off of the other side of the queue. And if it's a sort of standard line like a bank teller or the dining hall or something, the first person in is the first person out. But in a priority queue, you add things to one end, and the order in which you take them off depends on their priority. So the queue doesn't differentiate between those two implementations. So in order to write this interface, we don't specify the implementation. We just specify the interface, and then there are lots of different ways that we can implement it. So let's demonstrate that with a stack. Let's implement a stack using a linked list. And the key thing to notice is that the stacks have a push and pop as the key operation. And this should actually be really quick. So what we're going to do is we'll design the interface for the stack, we'll write some tests, and then we'll implement that class. I bet that we can do this in probably under 5 minutes. The way we're going to do it, though, is we're going to use the fact that we have a linked list already. So for a linked list, it's very efficient to add things and remove, for our linked list, it's very efficient to add things and remove things from the front of our linked list, right? Because if we add and remove things from the front of our linked list, we don't have to walk down the entirety of our linked list to find it. And so if we wanted to use push and pop, we should push things onto the front of our linked list and pop things off of the front of our linked list. And so by implementing stack with our linked list, yeah, it'd be great. It'd make our stack super efficient. Now think of the opposite, though. If we decided that when we push something, we put it on the end of our linked list. So then every time we push something, we'd have to walk to the end of our linked list. And every time we pop something, we have to walk to the end of our linked list. So that'd be really bad. That would be the difference between an order n operation for push and pop versus a constant time algorithm. So what we decide to use for our implementation can have efficiency impacts in how this ends up working out. Okay, so let's see if we can do this quickly. Anyone need to be re-added after our break? Okay, great. All right, so let's, just for the sake of clarity, I'm going to make a new package over here so that we can see where this new code is going. So new package, and we'll call it edu.westmont.cs30.stack. And in this package, we want to create a new interface, which is going to be for the stack class. It's going to be public. And this is pretty easy. There's only two things that stack has to implement, right? Push and pop. So push is going to be public. We'll use strings again, the thing that we want to put on our stack, and it doesn't return anything because we're putting it on. And then pop takes something off and returns a string. Some quick comments. All right, that's a little lame, but I'll do it. Add an element to the top of the stack. The thing to add. Remove the top element from our stack. Okay, interface done. That's the only thing we've got in our stack. I mean, maybe we'd like something like size. We could say size, maybe. Let's not overdo it. Okay, great. Let's stub out a stack so that we can write some tests against it. So a new class. We'll call it what are we going to use? We're using a linked list. My linked list stack. That's a bad name, but that's fine. And we'll use the my stack interface for it. Boom, boom, boom. Clips, do your work. Eclipse stubbed out everything in our linked list stack. And now we're going to write a test for it. We'll just write one test. Our test will be, we want a new stack. We'll use the interface as our type. That's going to create it. You got to spell it right. And now we'll say s.push. Well, let's see, what do we want to assert? We'll make sure that assert true that s.size is equal to 0. And then we'll push something on it. Tim, we'll push you on. Make sure that the size is 1. Then we'll push a large gorilla on top of you. We'll make sure that the size is 2. And then we'll push a cheese sandwich on top of that. And then, okay, fair enough. Then we'll push some dirty laundry.
Okay, but before we run this, can we change my name? So it's not me.
We'll just be clear. Okay. So that validated push. Actually, push, there's not much you can tell about push, whether or not it worked, because push doesn't return anything. It has a side effect. And the only thing that we can check for a side effect is that the size has changed. So we can do that. But now what we can do is we can pop the elements off. A stack also typically has peek as an operation, which returns what's the top element without taking it off. We'll just skip that for today. But what we can do is we can pop an element off the top, and we can assert true that the thing that we popped off the top is equal to dirty laundry. And I got to make sure I spell it right, or else it's not going to match. And then we want to make sure when we're done that the size is equal to 3. Dirty laundry. What did I do wrong? One more. Let's see. All right, let's just do one more to make sure that everything looks okay. There are a couple, yeah, great. Good start, right? All right, so that we're good to go there. So let's go work with our implementation. The way we're going to work with our implementation is we're going to wrap a linked list inside our class. So we'll say inside here we're going to have a private version of a linked list, and it's going to be our linked list that we used. And we'll just call that our data, maybe, and we'll set that equal to a new linked list. And make sure we import ours. Nope, there's ours, great. So when we push something onto our list, what we said is we wanted to put it on the beginning of our list, right, for efficiency. So we'll just say data.add onto position 0. Change that to what? We'll add what on. We don't return anything. And for pop, we're just going to say return data.remove position 0. And for size, we're just going to return data.size.
So why do they call it pop in there? Is it because it only removes the position 0 and nothing else?
That's right. Yeah, that's the idea of the stack.
And why do they call it?
For alliteration, maybe? Push, pop, peek? I don't know. Just, it's sort of like historical. So now we can run our test. Cross our fingers. Yeah, it passed. Look at that, it passed, and we exercised everything that's present in our current implementation.
Is this the first one that has 100%?
First, our array list did okay, right? But we had a bad test. Our linked list seemed to pass okay, but in fact that was a mistake. Yeah. So yes.
Unless there's a hidden mistake.
Right. So given that we had this data structure available to us, we were able to really quickly gen up a stack interface. Push and pop things because we had this linked list as a tool that we could build on. When we push things in, they drop onto a chain like this. If we were to drop our fruit from our test last time, blackberries goes in first, it's the last one out. So first in, last out. Or last in, first out. That's usually how you talk about it. So push and pop go in the top. All right, so what if we wanted to do the same thing with an array list? Well, we already have the test, so that's pretty good. Let's just take our test and let's copy it. My array list. And if we open that up, where's my array list? There it is. We just want to make sure that we implement that, not with, yeah, we want to make sure that we use the my array list stack. That doesn't exist yet, so let's go ahead and create it. Okay, it's stubbed out. Now if we run it, it's not going to work, but here's the thing. When we implement it with an array list, we have to think about what the underlying technology of an array list is. If we decide to push and pop onto the front of our array list, that's not going to be nearly as efficient, because adding things to the front of the array list means we're going to have to shift everything down every time we add something. Right, so then we're leveraging the properties of the array list. When we add things, when we push things onto our array list, we want to push it on the back. When we pop things, we want to take it off the back, so that we don't have to do anything based on the length of our array, except for the time when we grow our array. But that's amortized. Okay, so let's just do the same thing. We're going to have an array list, which is our implementation here. So we'll say a private array list. Call it data. That's going to equal a new array list. Going to import that from our implementation. Oops, there we go. Save that. And when we push something, we want to say data dot add to the end, so that's going to be data dot size, the thing that we're pushing. And when we want to pop something, we're going to return data dot remove data dot size minus 1. because if we have 5 elements in our array, the thing on the end is item 4, indexed by item 4. And to get the size of our stack, we'll say data.size. Now, in our particular implementation of ArrayList is great. All right, so that's going to be great. Okay, so now we run our test. Where's our test? My ArrayList stack test. Boom, passed. Coverage. So we're building up these data structures, and the more power we have in these data structures, if we have already validated that the underlying data structures pass these different tests, when we build on them, we can do these new data structures really quickly. So that's a stack with an array list. Designed the interface, wrote our tests, implemented the class. Same thing, same abstraction, but the implementation was different. Queues, very similar. Queues have add and remove as the key operations. We could do the same thing. We could just design the interface, write some tests, and implement that class. Let's just do this one way, though. Let's just do this one with an array list. And the difference is that we add at one side and we remove from the other side. So because of the way a queue works, neither an array list nor a linked list, the way we've implemented it, is going to win. Because if you add at one side, the linked list wins. If you remove on the other side, the array list wins. Because you either have to walk down the entire list or you have to shift everything down on one of the two operations. So with the two implementations we have, the add and remove, the time it takes, the efficiency of add and remove is flip-flopped, but they're equivalent in terms of one's order 1 and one's order n. Okay, so do it real quick. Make a new package for us. And a new interface. Not sure what that was about. Let's try it again. What goes in a queue? Well, we have something that we add. And we have something that we remove. Leave it like that for a moment. New class that is based on that. What are we going to use? An array list? There's our stubbed out class. There's our test. We just made one. We'll say q.add. Who are we putting in line here? We'll put cousin Jim, grandma, granny, and my crazy drunk uncle Bob. All right. So we didn't add a size to our interface. We could if we wanted to, but I think we're kind of getting the point here. What we want to do now is we want to assert true that q.remove. Again, there's no index here because things are going in and coming out. Cousin Jim went out first, so that better be equals to cousin Jim. And then we better have Granny. And then we better have my crazy drunk Uncle Bob. Okay, so that tests basic functionality. It's not going to pass because we haven't implemented it. To implement it, we will just have a private instance variable. Save that up. Make sure we import ours. When we add things, we're going to add them to, do we want to add to the front or the back? Does it matter? Adding to the back is going to be more efficient in an array list, but what does that mean for remove? Anything we do on the back of an array list is going to be more efficient, but the problem with the queue is we can't do everything on one side. We have to do one thing on one side and one thing on the other. So it's arbitrary whether we decide that adding is going to put things on the front or the back of the queue. Remove has to be from the other side, but we're not going to be able to get around the inefficiency. Okay, fair enough. So we'll add to the front, and we will return the element from the end. And if we run that as our test, boom, RAM, awesome. Again, because we had these data structures that we could build on. Queue is a little different. We can add or remove. We have to add or remove from one side or the other. This is an abstract kind of idea. This picture is an abstract representation of what we're doing. We could actually implement it with any number of different technologies down there, but we have to make sure that the abstraction meets. We could do it the same thing with a linked list, and we could just swap things out. I don't think that's really necessary for the point of the class, though. Process of designing the interface, writing the test, then implementing that class is test-driven development. There is a way to do a more efficient queue. There's a pretty good exposition of it in our text called a circular array. And what is different about a circular array is that it's like an array list, but it keeps track of a start and an ending position separately, so that when you add things to your circular queue, you put them in here, and when you remove them, you take them from here, and you update start and you update end appropriately. And so you always have these things moving along, and you never have to do any shifting, because the pointer, you have an index of where your data is good and where it's bad. And when you get to the end, you just move start around to the front, and then end wraps around to the front. So that could be a more efficient implementation, because if you're keeping track of it that way, when you add something to the beginning, or you remove something from the beginning, or you add something from the end, or you remove something from the end, you're just filling up the gray squares, and that's constant time. Circular arrays don't have any shifting until you fill up your array, at which point you have to allocate twice as big a space and copy everything over. So that could give you a more efficient queue if you were so inclined to do that. Okay, the last thing to talk about, and then we'll be done, is to talk about a hash table. And we'll just talk about it briefly. But a hash table is the underlying implementation of representing a set. And a set requires, the hash table in general requires a hash code. And a hash code is a fingerprint of an object, that whatever data you have in your object, whatever instance variables you have, no matter how many they are, no matter what you've got stored in them, a hash code takes your data and it represents it as an integer fingerprint, like a watermark of your data. So if your data changes, your fingerprint changes as well. And so Eclipse will write a hash code function for you, a method that is called hash code that will return an integer that represents or fingerprints your class. And you can use that in a variety of different ways. For example, you can use that to index into an array list or an array in order to get a particular element that you might be interested in. You do use it for encryption in different ways. You will use it to typically a hash code is used to test the integrity of encrypted data. Because what you can do is you can take all of the data that you just encrypted, you can create a hash of it, and then you can take that hash, and you know later on if you have a message and you decrypt it, you can take the hash of the message that you decrypted and compare it to the one that you looked at before. And if they're equal, then you know that the data has integrity. Because you can pass the hash code is non-reversible. So, okay, so here's the scenario. I have a message I would like to send to you. I have to send it over an insecure channel. And I want you to have confidence that you received a version of the message that's not been tampered with. So before I send my message, I'm going to take a hash code of it. So now I have a fingerprint of it. And I'm going to just send you the fingerprint. And I don't care if anyone sees that fingerprint because there's no way to recover the data from it. But you'll know what the fingerprint of the original data is. Now I'm going to encrypt the data and send it to you. And you're going to decrypt the data. And then on your side, you'll calculate the hash of the decrypted data. And you'll compare it to the hash code that I sent you. And if your decoded data's hash code and the one that I sent you are the same, then you have confidence that over the course of transmitting my data, it wasn't tampered with. Yeah, so the process of encrypting and decrypting is slightly different than what you do with a hash code. Hash codes are usually just used for validating the integrity of messages because it's like a fingerprint, right? You know that the fingerprint of the message is consistent. So roughly what you would do with a hash code is you would do something like the code here in the middle. You would calculate the hash of some object X, and you would store that in H. You'd take the absolute value of it, just make sure it's positive. And then in order to get the index that you wanted to look for that particular data in, you would mod it by the length of the array that you're storing data in. And that gives you a way of looking into an array to find any element that you might be trying to store in that array. If two elements end up with the same index, you can chain them together in a linked list that's stored in that element in order to keep track of it. So every entry in a hash table is going to point to a sequence of nodes or data like X that contain the element with the same hash code. And the important thing to draw out of this is that the hash code is a fingerprint, and that fingerprint can be used as part of building other data structures. All right, so in summary today, what did we do? We implemented our array list. We implemented a stack based on the linked list and the array list. Of course, implementing the array list took a little bit of time because we did the tests, we did the implementation, we did the correction of the test, and then the debugging of the linked list. We built a stack really quickly based on the availability of a linked list. We built a stack very quickly based on the availability of an array list. We built a queue very quickly based on the availability of those other data structures. Because we understand how those data structures work and what the abstraction is that they're trying to capture, and then we can leverage those to build other tools. And then we quickly at the end introduced the idea of the hash table, and I'll give you more options. And you'll have to read through that in the text to fill out the understanding of that. Okay, today's Thursday. That means tomorrow is the exam. Any last minute questions about that before we end for the day? You don't have to have them. So it's pretty equal coverage of all the different chapters, I would say. It's all multiple choice, 98 questions, 2 hours. See you here unless we've arranged something else. Okay, great. Break for today. Thank you for your attention. Happy Memorial Day and happy exam.